After this, maybe we will be ending for the presentation today here. Our next speaker, Po-Cheng Hsieh, Mr. Po-Cheng Hsieh. Only one word different from mine. We don't have any relationship, maybe not relatives. He is from National Taiwan University, and his topic will be automatic Piglet detection and the tracking in farrowing house using convolutional neural network. Okay, let's welcome Mr. Hsieh.
Hello everyone, I'm presenter today, and my name is Po-Cheng Hsieh, an advisor at Dr. Yang Fu, and I'm from National Taiwan University. And today my topic is automatically detecting Piglet key points using convolutional neural network. And this is my outline. I'm going to start with introduction. First is motivation. The production value of pork is the most in livestock, which achieved 767 billion Taiwanese dollars in 2021. Even though the pig industry is well profitable, there are still some problems annoying pig farmers. The biggest one is low survivability of piglet. The survivability of piglet is about 70%, which means 30% is piglet dead in the farrowing house. It decreases lots of production value, so it's very important to observe the health situation of piglet. Conventionally, the observation was conducted by farmers who normally patrol the farrowing house quickly throughout the day. To diagnose the health situation of piglet, it all depends on the experience of farmers. This way is too subjective and time-consuming. So my objective is to develop a system that can automatically detect piglet. In labeling process, I label 3 key points, which compose head, center point, and hips, and train the model to learn about it. If the model can predict these 3 key points accurately, it can be used to identify some behaviors of piglet. For example, heads can be used to identify the feeding behavior. Center point can be used to calculate the activity of piglet, and hips can be used to identify the tail biting behavior. If model can identify this behavior, it can help farmers to know the situation of piglet earlier and find a corresponding solution to solve it. And next is method. I'll start with framework. SLIP is a deep learning framework for labeling, training, and checking. It has convenient command line and GUI for users. And this picture is the system pipeline. First, we will put the video into the framework, and then labeling the data in SLIP GUI. After labeling, we will take the labeling data for training. After training, the model will output the post-animation of animal in image. And if you have post-animation, you can do the checking process. And I will going to introduce the training details step by step. And first is image acquisition. Video were recorded at the peak font and link code. Each video was 5 minutes with frame rate of 5 FPS. And due to the angle and position of webcam, objects surrounding the farrowing pen will also captured in video. So the image will created by perspective transformation. After creating the image, the transformed image will be put into the framework for labeling. Labeling was conducted in SLIP GUI. There are 3 key points we used to define the skeleton of piglet, which composed of head, center point, and hips. And I totally labeled 400 frames, 360 frames for training and 40 frames for testing. And I'm going to introduce the network training. This research has two models. One is centrist model, and the other one is centered instance model. And first, we will put the original image into century model. Century model will try to find out all piglets, and then cropping the image of each piglet. After cropping the image, cropped image will be put into the centered instance model. And centered instance model will try to find out all key points. As I mentioned before, there are two models in this research. One is century model, and the other one is centered instance model. Century model was used for detecting all centuries of piglets. Then, cropping the image of each piglet based on the centroid. After cropping the image, cropped image will be put into the centered instance model. Then centered instance model will try to find out all the key points to define the whole skeleton of the piglet. And these two models choose UNet as architecture. UNet is the simple encoder-decoder, which composed of convolutional blocks, downsampling blocks, upsampling blocks, and skip connection. Convolutional blocks and downsampling blocks was used for extracting the feature, and upsampling blocks and skip connection was used for reconstructing the image while preserving the feature. And the reason I choose UNet as my architecture is that it can easily change the number of downsampling blocks to modulate the receptive field value. And what's receptive field? Receptive field is the size of area that pixels on feature map mapped on the original image. And let me explain by the pictures. When you do a convolution, you will put a filter on the image to convert the image into smaller size. And after convolution, you can obtain the feature map. And as you can see, the 1 pixel on feature map 1 can represent 3 by 3 areas pixels on original image. So we can say that the receptive field value of feature map 1 is equal to 3. And if we put another convolution on feature map 1, we can obtain the feature map 2. And as you can see, the feature map 2 pixels can represent 5 by 5 areas of original image. So we can say that the receptive field value of feature map 2 is equal to 5. And why should we modulate the receptive field value? That is because the author of SLIP had done an experiment. It shows that different species of animals have their own fitting receptive field value to get the best performance of model. For example, you can look at this picture. X-axis is receptive field value. Y-axis is accuracy of the model. There are 3 kinds of animal: flies, mice, and bees. They all have their best performance in varying receptive field value. So this is the reason I choose UNet as my architecture. And this is my chaining details. Left side is century model, and right side is centered instance model. And next is result. Century models achieve an AP of 75.6%, and right side is the loss graph. And centered instance model achieve MAP of 34.8, and right side is the loss graph of 2 model. And you can see this picture, the x-axis is arrow, y-axis is part, and part A is the head, and part B is center point, part C is a tail end. And this picture tells us that part A and part C have large size of error. And what problems make this result, I will show you guys in discussion. In training process, I think that there are some questions can be discussed. First is image problem. You can see the area of this picture. There are two problems. First is the overexposed. It makes pictures have no details. And second is overlapping of piglet. It's very hard for model to identify which body part it belongs to. And second is environment problem. You can see the area of this picture. There are lots of piglets were blocked by obstacle. It's also very hard for model to detect the piglet which was blocked. And last one is insufficient training image. And this is my conclusion. Century model achieved an AP of 75.6%. And centered instant model was achieved an AP of 34.8%. And this is my future work. I will improve the model by increasing training data. And second, I will labeling the data more accurately. And last one, I will try to ace on augmentation for training. And this is my presentation. Thank you for listening.
Thank you very much. It's very interesting. And questions?
The MAP of your central instant model is quite low. Do you have, when you label in the image, have you followed any rule to label the head and tail of the piglet?
Yes, I label the head between 2 ears, and I label the hips on the outlier of the arc of the hips, like, let me show you. Like this, the arc of the hips and the between 2 ears is head, but I didn't label very well, so I will try it in the future work.
Okay. Second one.
I want to know the reason why you choose your training and testing data percentages 90% to 10%.
Because of the number of training, the total number of data is too small. So I can put more data on testing data because it's not enough for training.
Do you have any strategy to, like image processing method, to solve the overexposed problem?
Yes, maybe.
I will try to use some like get a background or something to improve the quality of the picture in the future.
Okay, is there anyone else? Okay, and time is up. Thank you very much. And that's the end of this section.